classes together with Jörg Sonnenberger, so you have to be with me. What I'm going to talk about, I talk about the motivation of support, the power management framework itself, the ACPI infrastructure work necessary to get this done. A special topic is the handling of video devices, and I talk about some of the work coming soon or whenever we'll find the time. So what is this about? Well, my laptop is my office. I really need it. I take it with me all the days, so it has to work well. A while ago, Lenovo stopped the APM support. Most other vendors didn't even have it for the last 4 or 5 years. So we really have to have ACPI support. APM and SMT don't play together very well. AMD64 is another problem. And of course, if you are traveling around a lot, you want your battery to last as long as possible, or at least as long as your journey is. That's quite a challenge. So, what do you want to have? Suspend to run. Ideally, whatever I'm doing, I can just close my laptop, suspend, and wake up and continue what I was doing. Should be possible to disable all the devices I'm not using to save power. And when the system can figure out if a device is in use or not, should be able to disable them itself and re-enable them when they are, well, used again. And of course, we need some way to communicate inside of the system to connect different components together and make the experience as pleasant as possible. I mean, Windows does get many of those things not right, but reasonable well, and we have to get somewhere in that direction. Linux tried it. In many cases, they weren't so successful either. We can do better, hopefully. So, PMFs, NetBSD power management framework, is one of the core components in this. It consists of 2 parts. That's the device interface, and that's the event interface. The device interface. Device power management is generally done by a combination of 3 different layers. One component is a device-specific logic. The second component is a bus-specific logic. The third component is a device class logic. I come to that back in a moment. The idea is when you do a suspend, you first call the class handling, then the device handling, then the bus layer. For the resume, you go the other way around. And important, if anything fails in this process, the whole transaction gets cancelled. At the moment, we are bailing out. We will make some changes to try to get back to the state we were in before, which is especially important if you try to suspend the system and it fails somewhere. You don't want to have a well, completely broken system if we can try to recover. So, but that's a bit future work here. One example of the bus handling is PCI. For the suspend, the infrastructure completely handles saving the generic part of the configuration space. It disables address decoding and bus mastering of the device as required by the PCI specification. Initiates the transition to the state. At the moment, we are using the hot state. Might be possible, depending on the bridge, to actually use cold state as well. For card pulls, we do the equivalent, we actually turn off the power to the socket when the last function on it is disabled. On resume, again, we turn on the power for card bus. We go into the D0 state, which is device on. And we restore the configuration space what we had before. FreeBSD does a part of that, but not everything is. Yeah. Yeah. One special thing on shutdown, we just disable address discoding and fast mastering. Solve some of the problems with partial reinitialization on reboot. When the firmware doesn't deal with it very well, for example, when the firmware doesn't initiate a PCI reset, active devices could just randomly corrupt system memory. That's very unpleasant. One example of class-specific actions are network devices. Basically, the driver tells the system, okay, I'm a driver for this network interface. On suspend, we call the IF-stop routine. On resume, we call IF-init and IF-start if the interface was up. There is logic in some of the drivers to disable the device when the interface is turned down. We had a lot of this ad hoc in the cardbus layer. Now all the devices that support this kind of thing do it in the generic bus independent code. It just works. And the interesting part is just the first action is enough to cover almost all the network drivers. A few of them need to have a bit more logic necessary, like saving and restoring specific PCI configuration. But for almost all the drivers, you don't have to do anything special. That's very handy because it reduces the amount of duplication in the tree quite a bit. Another good example of what you can do is generic audio. It's a generic audio class handling. First of all, NetBSD is audio driver has a special child, which is the actual instance in the audio tree, and which corresponds with the instance of dev audio or dev sound. And we actually use this relationship to simplify the code. When you suspend the audio device, it goes to the corresponding physical device and says, okay, give me your current music settings. Stop whatever you are doing, like playback or recording. And resume, well, start it again. We had some problems with some drivers where this doesn't work correctly, or USB is currently a problem in that area, because when you want to do the next thing, it's nice to be able to power down the audio subsystem if it's been unused for a while. Like I said, this doesn't work for the USB code, because the USB code has an async interface, and the problem is you can block for quite a while, and you don't want to do that from a call-out handler. We are not exactly sure how to best address this yet. Most likely, the idle handling will move into a separate kernel stack, which would work around the problem. It's not the best way, but yeah, we are thinking about how to improve that. And we also have event handlers to increase and decrease the volume, mute it, turn turn it back on. More about that later. The system interface of PMF has three different components. The lowest layer is the PMF device suspend, PMF device resume function. That basically just does call the class handler, bus handler, device handler in the right order, and bail out if it doesn't work. It also does logging on the system tree so that you don't have races between different components, one trying to shut down the device and the other one trying to turn it back on. That had some nasty problems in the ACPI system, where the audio process in userland was already trying to play back the card when the other CPU was just trying to reinitialize it. That wasn't fun. Had some interesting problems. This is fixed that way. One layer higher are the functions to actually deal properly with the tree structure. So because of suspend, you give it the device and make sure that this device and all the children are completely suspended. The resume functions have two different versions. One, I give you a device and resume this device and all the parents' devices that are currently not actively usable. The resume subtree function does equivalent of the suspend. Resume this device and all the children. And the very high level functions are system suspend, system resume, and system shutdown, which are the machine independent part to suspend all drivers, resume all drivers, prepare the system for shutdown. PMF system suspend first checks whether there's any device in the tree that doesn't support PMF, in which case it complains and bails out immediately. So if you want to have ACPI suspend to run, all your drivers have to support PMF, otherwise it will just complain. It's nice in a way, it tells you which devices are problematic, so you can disable them and complain about them. But what we didn't want to have was a situation where the system just randomly crashes because some driver doesn't implement the necessary hooks, and but there are quite a lot of drivers that still don't do it correctly, so we needed it that way. The event interface is used for communication between drivers. You can send an event notification to a specific device or the whole system. The primary example for using it are hotkeys. And when thinking about it, a solution entirely in userland was considered too quirky. You can do that. I mean, it's kind of what Linux is doing with Hall. And there are a lot of issues associated with that. For example, figuring out the devices that are involved. You have some actions you want to react to as soon as possible, and there are, for example, when the battery is running low, you want to do something intelligent in that case, even if the user doesn't have power unit running. So the same applies here as well. We do expose events to userland using the system monitoring framework. What we currently don't have is a way for the userland to trigger an event itself, but it's just a question of time. What we currently have are events on lit volume handling, I mentioned that earlier. If you have a sound card in the system and the fancy magic buttons handled by your system-specific ACPI controller will just work. And of course, making the display darker or brighter, on and off. So this was a generic side of the BMF framework itself. I'm now coming to the ACPI part. Are there questions so far? Okay. So what did we need to do for ACPI? First problem was the ACPI CA, the component architecture we used was quite old. It was from, we were using the 2006 version, and it had a number of problems with newer laptops where the firmware actually started to use ACPI 3 features, and we needed an update for that. One problem we had is for the new ACPI CA, we needed to make the embedded controller MP safe. And of course, we really needed ACPI suspend to run support for AMD64 and SMP systems. For the ACPI update gave us many bug fixes in the newer releases. But there was an interesting problem. We know that there was a newer release because FreeBSD was using it, but it wasn't available for download, just in a quite older version. This has changed in the meantime. Maybe it was just bad luck. So we did just take what FreeBSD had in S3. So there were a lot of functions that were changed. Some were renamed, some got some new arguments. This is mostly mechanical work in the drivers. Yeah, but it could have been avoided. Some of them were for no good reason. And of course, we had to work on the embedded controller driver to get it work with a new word order. We had an interesting problem with the ACPI initialization because interrupt routing table, which tells you how hardware devices are mapped either to the old PIC or the IOR PIC, was not passed early enough, and when ACPI CA wanted to set up the system configuration interrupt, we didn't have that table present at that point. Fortunately, the code deferred the interrupt setup and just processed it later, but that was nasty code. Made all the things a lot more complicated. Well, there was a way around that. Do the processing in various parts. First of all, just initialize the system so long that you can actually pass the MADT, which is where the interrupt loading is described. You have to pass system description tables for that. You have to set up some mutexes, but that's it. Well, pass it and continue with the rest. This dropped like 200 lines of code or so from the ACPI support infrastructure by removing all the need for this deferred interrupt setup. And well, now we have two functions called instead of one UPS. So there's this piece ACPI embedded controller. What's this? ACPI is a virtual machine, and this virtual machine needs to access the hardware for a number of things. For example, if you want to carry the battery, You normally do that by using the embedded controller. When I say slow hardware, I really mean that it can take a few hundred milliseconds. It can take a millisecond in some cases, and you don't want to pause the hardware if you don't have to. A second part of what it is used for is to inform the system about the hardware state. For example, if you plug in the PCI Express card on a hot plugging system, you might get an ACPI event for that one. The hardware protocol itself is quite simple. You might know this microchip. This is actually the keyboard controller. And I have this slight impression that when they wrote the ACPI specs, they wanted to reuse these chips from the 1970s. That's how the protocol looks like. What we basically have are two 1-byte ports. One of those ports is used for to send comments to the controller and to read back status information. The other one is used as combined data and address port. There are a number of comments you can send to the controller. The first one, the query command, is used to find out why you just got an interrupt from the system. Ignoring that is a bad idea, as it will just continue to interrupt you, not fun. When you send it that comment, after a while it will come back to you, okay, I just figured out what I wanted to tell you, read it from the data buffer. The read comment, well, you write the address you are interested in into the data buffer, wait for the embedded controller to process it, and well, in the same register, afterwards you can actually read the data you are interested in. Why it works, just the same. There are two commands, enable burst and disable burst. They're used to simplify and speed up processing. Basically, you say to the embedded controller, okay, give me your attention. Stop whatever else you are doing, process those commands as soon as possible. FreeBSD is using that, Linux is using that. The problem is it doesn't work on some hardware. So you might have problems with it. And even worse, using the burst mode makes the whole program a lot more difficult, because the embedded controller can just decide, no, I just don't want to talk to you, and turn off the burst mode itself. Hardware is fun. So what did we inherit from FreeBSD? It's a mix of polling mode and interrupt code. The code paths are just looking like Italian pasta. And
Italian pasta.
The long one. And figuring out how to do correct locking in it was non-trivial, especially if you wanted to guarantee that there can't happen a deadlock. After looking at it for a while, having a prototype with correct locking, I was looking again, okay, this must be possible to do easier. So I sit back and wrote it again. So the first component we have is there's a kernel thread that just processes the system configuration interrupt. It does nothing else. The second part is there's a read function and a write function. That's a public interface used by ACPI, CA, and other drivers. For example, for ThinkPads, there's a special driver to turn on the sync light and other things like that. There's an exclusive lock on those 3 entry points. That's the first part of the logic. this exclusive lock actually might be two locks because ACPI in some cases as a global lock you need to hold to serialize with the hardware as well. I don't know why they invented that part. You have to deal with it. And there's a state machine that contains all the really interesting logic, and you can use it two ways. You can use explicit polling modes, that's what we do during booting, or you can use interrupts and make the interrupt handler just right. A state machine looks something like that. At the beginning you are in the free state, and on each interrupt basically you go down to a different layer. That's it. Well, problems. This was too simple, and like I said, hardware is nasty, especially this piece of hardware. There's some hardware that doesn't like to be pointed in a tight loop. When I was doing the first version on it on my ThinkPad, and I had a wrong condition in it. I couldn't turn off the machine. Normally the ACPI specification says you have to have a fallback mode on the power button. If you press it for something like 3 seconds or 10 seconds, depending on the hardware, it has to switch off. Well, it seems IBM decided, oh, we can do that in the embedded controller. Now the embedded controller was busy reacting to my code. It didn't turn off the machine. The only way you could shut it down was cut off all power, including the battery. Nasty. So we had some other problems with the embedded controller returning bad data when called too tight. So basically 100 milliseconds for tight loop is a safe value. What we actually do in the code is we call with a 1 microsecond delay for 5 times or so. That's enough for most comments to succeed. Otherwise, we back off either to interrupt-driven operation or to polling with a longer delay. That fixed one major issue. The other major part is you might not get interrupts when you expect them. That was the reason why Linux switched to burst mode. But it can be done much simpler. So we don't get interrupts from the hardware, while we have a generic mechanism in the kernel to get back to us. Just schedule a call out to the next tick and keep the state machine a bit. It works surprisingly well. It's like 10 lines of code and it completely fixes the problem. So with that, all the known problems have been fixed. It works in all the situations we have currently tried to use it. And I think it's quite easy to add new workarounds if a problem does appear. Code size is about the same as the old driver without the huge Intel license. That was another reason to rewrite the code. I mean, having 4 or 5 pages of license at the beginning of a file is not fun. There's something missing on the header line. Suspend support. What did we add? i386 support only, 32-bit, nothing more, and only for uniprocessor systems. Well, you have 2 choices, APM or ACPI S3. APM is essentially dead. We didn't really want to break it, but we got a number of bugs. We got at least 1 bug report for APM. I'm still looking into that. But the real thing we wanted to have was ACPI S3 support on all the systems if possible. clean up the code we had. First of all, it used something that surprisingly looks like a set jump and long jump. And it used a lot of inline assembly. Don't do that, that's nasty. The register saving and restoring was moved into a separate function, pure assembly, separate file, easy to compile. Yeah, no GCC dependency here. The second was this set jump, long jump semantic can be turned into much cleaner code flow. Basically, ACPI empty sleep as a backend function invoked by the system. This one calls prepare function, which saves the register and goes back into the C code that does the actual call to the ACPI infrastructure. On resume, we end up at a different point, the exit function. This one goes back to the C code. And so we basically hide this implementation detail of a different return path completely in the assembler code. And the higher level C code doesn't have to do about it. One real advantage about it, we have to save less registers because API says you don't have to bother saving a number of them because the caller is responsible for them. The next good idea is make the assembler code as simple as possible. So the low-level assembler stuff, which is called in real mode from the CPU on resume, was trying to be position independent code, which is nice, but we don't need it. I mean, we have the full control of how we want to lay out the real mode address space. So let's just do that. Offset can be handled using the linker. What else? Makes it simpler. The second interesting part is when you want to switch to protected mode and you want to enable paging, you need to have a page where the virtual address and the physical address are identical. Originally, this used a very, very bad hack. It forcefully switched to the kernel map, entered a page in an address space that normally belongs to the user space into it, and switched back on resume. I actually did something much simpler. Just copy the page table and create an entry for first 4 megabyte of the address space inside it, where you just put your identity mapped page inside, and on resume the normal restore of the control register 3 takes care of moving back to the kernel page table. And of course, in the low-level code, only initialize what we really need to have. For example, we don't use most of the segment registers, just keep them in whatever states they are. The interrupt descriptor table is not needed at that point either. We're later switching to a new global descriptor table, the one the kernel normally uses, and we can just move that to that point as well. The global descriptor table itself can also be reloaded just after we set up our temporary mapping and back when we are in our normal kernel code. One thing that really hit me was when Yamamoto-san merged the large page code into a head, which always makes the kernel use 2 megabyte pages if the CPU supports them for the code segment. Well, what do you get if you want to jump to 2 megabyte page when PSP is not enabled? A segmentation fault or something like that, which is not fun when you're at a point where you can't really handle exceptions at all. After that, I started to work on the AMD64 support. First of all, when I did set up the temporary page table before, I was making my job for AMD64 a lot easier as well. Because on AMD64, when you want to switch into the long mode, you need to have a page directory, which is now called something else, but that's essentially what it is, which is still addressable in 32-bit mode. So it has to be under 4 gigabyte, but real mode certainly is under 4 gigabyte. The bootstrap now contains of 2 parts. First, you move to protected mode without paging. Afterwards, you enable long mode and paging. Another nice surprise was you have to enable the no execution bit early. That hit me when I started to work on the SMP support. I come back to that in a moment. But otherwise, the code is very, very similar. You have a number of registers you have to restore. Some of them are 8 byte long or 4 byte long, but overall, most of this is just copy and paste. So what did we need to get multiple processors or multiple cores working? Well, first of all, when suspending the systems, you just deschedule all jobs from application processors. Next, you force the application processors to save the current FPU state. It doesn't happen normally, lazy FPU switching. Instead of using global variables, we put the registers into CPU info. And we actually use an API to save the other application processors in the low-level code. We restart the application processors individually by using just the same wake-up code we use for the master processor. The only real difference here is the other CPUs don't do any virus handling, and they don't try to be. That's it. One interesting problem I was hitting was when you first tried that, the application processor, in this case the second core on a Intel Core 2, just panicked as soon as it was woken up inside the idle switch. And that didn't make any sense at all. Even worse, the values I was seeing from the code differed from the values the first core was telling me. So yeah, cache coherency is nice. The problem in this case was when the second core was shut down, it never did an explicit cache invalidation. So the last change it did was mark the idle thread as unused, and that one got lost on the suspend. Write invalidation on a core 2 doesn't affect the level 1 cache of the other cores. Yeah, after that, it worked. So let's talk about something interesting. The biggest remaining problem to use it on many modern systems is how to deal with your hardware. Well, luckily, all the strange chips are essentially dead. No more stupid old chips. But there's so many incompatible graphics chips out there. How to deal with them? Many of them are not publicly documented at all. There's some work in the DRM layer to initialize the graphic chip completely inside kernel code, and to be able to set specific modes, but it's not really usable, and it will only cover a small part of the more modern chips. For some systems you are lucky, it will just work. For some, you can trick them by setting a BIOS password, and it will do the necessary magic. On some, you can actually, before switching to protected mode, just kick the VGA BIOS to do a power on self-test and initialize the hardware like it would do during the normal boot. Some others just crash when doing that. So, what do we want to do now? On most systems, it does work if you do a post. One problem is if you want to do that, the PCI will just have to be initialized again. That's a problem on the Dell machines because it doesn't do that. It doesn't have to, so why should it do that? One approach is emulate the real mode and just call the VGA BIOS again. There are two approaches for this. The tool works entirely in userland. It either uses a normal virtualization feature that's only for IFE86. The M86 mode doesn't exist on AM64 mode. Or otherwise it uses software emulation. Problem is, it doesn't help you much if you want to actually debug resume code. And giving userland access to the physical memory and the I/O ports necessary comes with some security implications. So the question was, can we do it in a better way? Well, yes we can. I started to take the software emulation code from the tool, which in itself was taken from X86. It was donated some years ago by Skytech. And yeah, it allows doing pretty much the same thing the tool does entirely in the kernel. Well, of course, it does make the kernel larger. And if you actually have a problem with a VGA BIOS, it will crash your complete kernel. Well, sad. So about the size, we are talking about 80 kilobyte of compiled code. That's a massively rewritten version of the original code, which is originally was something like 200 kilobytes. It's small enough that you can actually put it into a bootloader. I do have some code to emulate some important devices, for example, the timer code. In Dragonfly, we had this funny problem with, when using the Visa frame buffer, that some BIOSes like to play with the second timer. And if you want to use the second timer for actual timekeeping purposes, it's not nice if the BIOS overwrites your settings. So what I did here was just emulate it in software. A nice second use for this code is, who in the room ever had panic when inside X11? What did you do? Well, you have a problem. If you are lucky, you have a serial console attached or something like FireWire or so. Otherwise, you can hope that the message survives, but otherwise not nice for debugging. So what we can do with this code is we just keep the BIOS again, reset my console, and at least we are back in text. It doesn't work on all systems, but it works again on quite a lot of systems. And of course, it can also be used to make the frame buffer code machine independent. We have a summer of code project for that, so if you're a student and you're interested in working on this, be my guest. So what else is there to do? We currently don't use the C states of modern processors. Hack for Core 2 shows that the overall battery usage goes down by 4% when using C2 in the idle loop, and for 8% by 8% when using C3. There are some problems with using especially C3, because when you use C3, the local APIC will be shut off, and it's not nice if you're waiting for a timer interrupt from the local APIC to wake up again. That's one of the reasons why I never committed that patch. The second major problem we need to work on is suspended file systems. We do flush all dirty buffers before going into suspend. So we could, for example, for the fast file system, mark it as dirty with a special second marker to say, okay, this was in a suspend state. So if the box doesn't come back from suspend, the file system check can just mark the file system as clean. Also, it's important when you want to do suspend to detect if something else messes with the file system in the meantime. You could put something like a random cookie inside the suspend block, and thereby detect whether different operating system, for example, had mounted the file system viable and changed something. The third area that needs more work are low power states for devices. A number of devices can have something between shut off and fully running, and doing that can save quite a bit of power. Of special interests are USB and FireWire. For example, on this machine, power consumption goes down by another 10% compared to the darkest display power state and otherwise idle system. And one of the interesting things to look into is whether you can get events from the USB controller or the FireWire controller when a device is connected. And if you can, and you don't have a device attached to them, you can just put the controller into sleep mode, which hopefully takes a lot less power. And of course, the last point is suspend to distance mode. Questions? Yes.
One of the issues I've had when dealing with power shields for USBs in the distant past is interrupts. I'll have to do special things to turn off interrupts to keep the system from going into an interrupt store. You guys have to do anything similar?
The question was when you use suspend or remove, how do we deal with interrupts? We have function that tells you which state the device is going to be, whether it's fully suspended or only the device class itself is suspended. Basically, for PCI devices, that means you can check whether you are allowed to access the PCI registers. And if you are not allowed to do that, you know this interrupt isn't for me anyway. So you can shortcut the interrupt handlers, and that solves all the problems we have. There was there's one area where we have to be very careful. When you have USB host controller, there's this fancy thing called legacy mode, where the BIOS provides some emulation of the classic keyboard and mouse interface. And we had to find out that turning off interrupt notifications and turning off legacy mode can turn on the interrupts again. And that's something to be aware of, but otherwise there wasn't really a problem.
A second question. One of the things that we've talked about in FreeBSD is automatically providing power hooks of some variety if you fit the interface up or down. Is that one of the things that the plastic mechanism we talked about at the beginning of the talk does, or is that a future enhancement?
The question was about providing automatic power handlers when, for example, for network interfaces.
It's a lot of times you want to do.
Yeah. That's the second item from the bottom. Basically, it does need some support in the driver, but it's very easy to enter. We haven't done it in the generic network layer for two reasons. First of all, we currently don't know how to go back to the device from just given an ERnet pointer. And the second reason is that when an interface is put up and down is not so easy to answer because there are some interesting interactions. The IOCDL code is very brain dead in that regard. Yeah. So yes, there is some code, and we want to reduce the duplication necessary in the drivers as much as possible. It's not perfect yet, but works reasonably well. Other questions?
Of the time you've spent working on the code, how much of your time has been consumed by hardware bugs, ACPI bugs, and NetBSD bugs?
So the question is, how much time of developing this was spent debugging issues of various components? ACPI surprisingly most newer laptops actually have a pretty reasonable ACPI implementation. So you normally don't have to spend so much time on that. And a large part of the debugging work for that has been done by Linux guys already. Yeah, Linux is useful in some cases. So what remained were hardware bugs. And yes, I spent quite a bit of time because it's surprising when something doesn't work as advertised. And some of those problems are, for example, in the suspend path or the resume path, it's quite difficult to get any useful information outside of the system. I mean, how do you debug if you don't have, if you can't do a printf, or if you can't just write something to a serial console ASAP? There's one useful mechanism, just turn on the PC speaker and use an infinite loop. And if you want to know which of the places you did that was actually triggered, just remove the PC speaker. That works. It's time consuming, but it works. NetBSD bugs, not so many either. Part of the problem here was that I had to start writing proper power management support for all the devices I had and needed to use. That was somewhat time consuming, but well, it has to be done at some time, and I just had the bad luck that I often was the first person to do that. So I wouldn't really count that. really surprising was a problem with flushing the CPU cache. That took me quite some time to figure out what was going on here.
So, since the big bald guy is standing at the front of the room, we'll have to take all the rest of the questions offline because we have one more thing after this. So let's thank the speaker. Lightning talks we talked about last night in a couple of minutes. So stay tuned. Two talks, the lightning talks, because only two people sent this now. So the first one is Warner Ross talking about the current status of FreeBSD on MIPS processors, and then after him we'll have Alistair talking about NetBSD features. So you get 10 minutes at least to do this.
Actually, I think mine's going to be probably less than 10 minutes, so Alistair can run more. A lot of people have been asking me about what the current status of FreeBSD MIPS is. It's a new port of FreeBSD to the MIPS platform. Right now we have it including multi-user in hardware and on the emulator, GX symbol, and on Cavium hardware. We have dynamic linking working, so we have a fully dynamic root that we're booting off of. The test programs we've done so far are working okay. The build world seems to be going okay, but we've just recently gotten to this stage, so we haven't made any performance benchmarks. ACPI code is written, but not yet enabled, not tested. We've had a few issues with baking cells that we're in the process of resolving. Once we've got those issues resolved, it will be committed to the CVS repository. We're hoping by the end of next month. The hardware that we're targeting is primarily MIPS 32 and MIPS 64 ABI, both the initial revision and R2 hardware. The Cavium Octagon, the ADM 5120, and the MIPS 4KC processor and GX symbol have been relatively well tested. Those will work when we do the integration. The others I've listed up here are things that people have written and are in various states of testing and debugging. We don't have this hardware, so we haven't been able to do this. There are primarily 5 people working on this right now. Myself, Randall Stewart, Alexander Sherminko, Olivier Hanchard, and Wojciech Kozek are the people that have been working on it. So that's probably a good place to stop. Are there any other questions about this that I could answer while I'm up here? Simon. Right now we have a 32-bit VMAP, and we're jumping through all the hoops that you have to on Cavium because they have 64-bit hardware. Or hardware that's mapped to 64-bit addresses that you can't, it's too sparse to use TLB wired. We can use as much RAM as we can accommodate in the system right now, and we definitely use more than the MIPS direct mapping area. We've added code to make sure that we can map stuff above 256 megabytes. The Cavium boards have like 8 gigabytes of RAM, and we really want to use that. It speeds things up quite a bit.
So, I know the Cavium boards cost a fortune. What's the cheapest board someone can hack on this?
The ADM Tech boards are very cheap. I got mine for $30 at CompUSA back when they were selling hardware. Once we have everything committed, one of the things we're going to do is try to find additional inexpensive boards that are available today. The problem with the low-end boards is that they rotate out very quickly, and they tend to rotate behind brand names. you might have a router that's being marketed as the ABC123 router, and you go into the store and you buy it. Oh great, it's MIPS, and then you get all this work done, you tell people about it, and they go to the store and buy it, and it's some weird ARM processor because it's provision B3 instead of provision A1. So we were wanting to get everything into the tree as quickly as we could, and then try to start chasing after the different types of hardware that's out there. There are actually several MIPS-based wireless access points that are available that will target and supporting. Most are Broadcom-based. So we'll just go from there. That's true. That's true. And two of the different router boards, one's based on the ADM tech, and one's based on the IDT, whichever, the IDT R32 or 34. I don't know if that one's still available or not, but one of the guys that are working on it has that board. So that's what we're targeting. Good advice, thanks. Anything else? Okay, thank you very much.
About 9 days ago, NetBSD was 15, and on that occasion we decided to release some know-how, which are blueprint, a picture where we are at the moment, where we're going to be going over the next 18 months to 2 years. Obviously, based on a number of things. First is performance, security, innovation, and multi-core. Yeah. And of course we deliver. And you probably can't see it, but at the end of the rainbow, something called the beer store. Okay, there are 4 elements to our roadmap I'm going to share with you today. First one's storage. You probably heard me waffling on this morning about iSCSI. There's a number of other things that we have. So what I'll do for each of these elements is tell you where we are at the moment and where we hope to be the 5.0 branch, which we expect to do at the end of May. So that's 2 months for all the developers out there. If you want to get stuff in, get it done by the end of May, please. Firstly, puffs and putter. Auntie took us through that yesterday. Refuse, we mentioned that as well. I'll leave out the good old Umbra and Dimensional Rump. Rate frame we've had for ages, but it's worthwhile mentioning. It's an inherent part of our storage story there. iSCSI target and initiator. Cryptographic device, the file system switch, which is a way of doing snapshots based on for the fast passes anyway, and wedges, which are our very lightweight way of doing. How do I say? This is basically your package actually. More, we've got both. It's the past user space devices. There's a DevFS which will be going in soon, already in a branch in the repository. We've got journaling functionality for FFS handling the native out of Savvy systems. Physical block logging, right ahead, it does metadata only. but it is absolutely brilliant to be able to sit there and watch file system landing an FSCK moving back. We're looking to have the native ZFS port in there. Whether it makes it or not, I don't know. Maybe asking a bit of it. We've got every file except for 8 of them in the block IO there at the moment. Fuse low level and refuse low level. I hope to get that done by the end of May. Whether I do or not, another thing. If I don't, then it'll be in 6.0. I think the next one will slip as well, which is web-based management tools for storage subsystems. But I do know that Matt Thomas doesn't want to get support for flash devices in, and there's a guy in Holland who wants to get the rewrite support for UDF file systems in, and he confidently assures me it's 80% done. He has for a while. Plan for 6.0, which is going to be another year off. We're looking at object storage devices from T10. That's something that's built typically on top of AsiaBSD, and is a different way of doing file systems where much more of the intelligence is placed in the target devices. We're looking at doing basic FCIP support as well. That's fiber channel over IP for want of a better term. And we're looking at bringing in some new file systems as well. Right, virtualization. You probably saw from Christoph's talk earlier that we've got Zen 3 running. We've had that for a while on DOM0 and DOM-U, so that's the host of the guest domains in VMware terms. Just recently, what Manuel Boyer has done is the physical address extensions for DOM-U. Typically, if you go out to an ISP and you try and buy some time on a Zen host, they will expect you to have a PAE DOM-U. That's been a problem for us for a while, but Manuel did some marvelous work in getting that running. Also, he did the AMD64 board as well, so that's marvelous work there. We plan to get NetBSD user mode, which is an interesting one, but I'm not sure how far along it is. It's a port of NetBSD which runs entirely in userland. Interesting. It's in the source repository at the moment, and I'm not sure how far along it is or whether it'll make it for 5.0, but it's certainly something to look for if you're interested in that kind of thing. Yes, another way of doing the virtualization we're talking about. Virtualization jails, the second model, that's Christoph's chaos jails. We certainly hope that's going to be by the end of May. Thank you, Christoph. Right. What we plan to do for 6.0, again, that's a year away from branching, so we're looking about 18 months away from actually having something released. We're looking at iSCSI booting, iSCSI device cloning, which is a way of doing copy and write for iSCSI. And there's some other tricks we can do as well. I didn't mention this morning. We can do copy and write logs at the target end for that. We can do delayed copying of things, so we can actually have a stream of changes in a serial list. Do things like that. There are other things we can do with iSCSI as well. We can do remote mirroring of disks, so we can have RAID 1 across that. We can do hotspot backups, that kind of thing. All of that kind of thing is planned for 6.0. DOM-U migration, so amongst the VLAN, you can migrate DOM-U between physical machines, keep them running, suspend and resume it. The Blender driver support is where you add more memory to a new instance, so you can add more memory if it as and when it's needed. There'll also be some kernel changes necessary to keep that going. The network. Mobile IPv6, again, that's in a branch in our repository at the moment. We're looking at the selective acknowledgement stuff, that's in there as well. Plan for 5.0, and then the person I said was doing it suddenly decided he wasn't going to do it anymore. But I have got another victim lined up, so not to worry. Whether it gets in or not, I'm not sure, but at least we're planning on it, looking at it. And network driver pooling as well. If you want to find more about that, then please ask Matt Thomas at NetBSD.org. Right. He was the guy that wrote up the networking side of things. We got the OQ processing on input, integrated multicast DNS and zeroconf. Zeroconf in general would be nice to have with a decent license there. TCP support in libSA, and netbook from HTTP, which would be another interesting one, I think. Finally, the system. You probably know that we've had one guy working on what we call targeted development. So the NetBSD Foundation is actually paying him, and has done for the last 10 months or so. This guy is Andrew Doran, he's working out of Ireland, and he's been doing some marvellous work on SMP and removal of the giant lock from most system calls, and I won't bother showing you the picture again there. And he's been doing the implementation of putter and refuse, so there may be some duplication here because these are separate roadmaps that have been putting together into one. The new file systems that Antti has made there, the chaos secure model enhancements. They're in 4.0 already, but there are some other interesting ones coming down the line. I've got a role-based access control one, which is not ready for the light of day yet. But it's built on chaos, and that's a very interesting system to use, actually. There's an awful lot you can do with chaos, which I didn't realize before I actually set out to work out how it did things. The direct rendering manager, yeah, we've needed that for a while. We've had it for a while as well. So that's great that we got that in. I'm told that should read asynchronous I/O, so we take the POSIX out of it because we're not completely POSIX compliant. However, we've now got the asynchronous I/O and the POSIX message queues in there as well. And white curses, that's curses for white characters. That was originally done as a Google Summer of Code project. We've grown an SGI EFS file system. EFS is the one that came before XFS, so it's kind of old technology now, but it's still quite useful to have. It's an extent-based file system, and it's been in the tree now for about 6 months, I think. There's a new one-to-one threading model that we have. We've said goodbye to the old schedule activations, which were neat and worked very well, but had certain corner cases that we couldn't predict that weren't that great. So we've gone to a much simpler, much faster one-to-one threading model now. RUMP, I've mentioned it 3 times already, moving swiftly on. Raga, in one of the Nordic countries, has made the portable C compiler his little beast. And we've got that in the NetBSD repository. It's come along well. We pulled in J.E. Malik from FreeBSD. Thanks, guys. Good piece of work there. We've also grown a new scheduler. It's an N2 scheduler. It's meant to be processor aware, cache topology aware, that kind of thing. Another Google Summer of Code is the automated testing framework there. It's written in C++, but it's still pretty good. There's a bootloader configuration file now, so if you want to have your splash screens up there and other things like that, then yeah, that's there and working. Kernel Power Management Framework. I'm into Robert Watson mode at the moment, but just don't have the ability to do it and speak quite as quickly. Thanks, Jörg. That's in there and working very, very well. And I thought the demo was quite good. We've tried in the address space layout randomization support. So if you want to have that on, you can. Personally, I think these would caches and not perform that great, but it's there if you want it, if you feel strongly about these kind of things. So the other stuff we've done, we removed systrace. We didn't feel it was secure enough to have in the kernel, even if it wasn't activated and things like that. It worked well for a while. It's an interesting piece of work, but the problems are there, and we didn't feel the right to offer that. There's a performance monitor-based profiler. Thank you, and what is that? Pretty good. And Simon is still crying into his beer about the PC532 core removal. We've grown some mini dumps, which are interesting. They're sparse kernel core dumps, and they drastically reduce the amount of memory or file store that's used to get a kernel core dump. Very useful, and donated by one of our corporate customers, I think the way to say. Right, processor sets and affinity. Some of you know I used to work for Amdal. The big speed up that we got there when we were doing the tuning on the multi-processor stuff was by using processor sets and affinity to make sure that things ran in the right cache whenever we could, and also by changing around structure fields to make sure we reverse cache lines. So we're looking to some interesting speed ups and interesting performance gains from the processor sets and the affinity we get there. The real-time extensions for Liberty Thread. We've got scheduler control, which controls the scheduling of processes and threads, and kernel module support, again, which we've kind of grabbed off FreeBSD. Andrew's called it modules, and that. Almost there. I think this is the last one. Maybe one more. All platforms have been converted to use time counters. Again, that's the FreeBSD work that we're looking at here. We've grown OSS audio support for Compact Linux 32. Since OSS audio made their stuff into open source. Probably the crown jewel of 5.0 will be the NOP game improvement.
Is that in the kernel now?
Sadly, not backwards compatible. Well, certainly saving of games. Switching to DDB from a VGA X11 session. That's probably not English, but you heard Jörg talking about it about 10 minutes ago. Modularized scheduler. So we can actually have not just the BSD 4.4 one or the M2 one, we can actually bring in other scheduling models if we want to do some research there. New kernel concurrency model, new kernel linker, I think I talked about, and System 5 IPC tunables, where they're no longer statically defined, so if you want to view DVDs and things like that, you no longer have to build a custom kernel. Right. Virtualized gels via seg model. Journaling functionality, talked about more system calls made MP safe. I did a quick count last week. There were 26 system calls that are still to be made MP safe, and that included all the LFS, the iTimers, and KQ and K event. I saw over the weekend that KQ and K event have been made MP safe as well. We're down to 24 at the moment. I see some more mods that are out there on the mailing lists, asking for people to look at some of the socket calls as well. So, for only some of the domains, but it's still more improvement. Down to 24 calls that are not MP safe from 200 nodes is pretty good work, I think. We've got full kernel preemption for real-time threads. One of the branches that has just hit the source tree at the moment for 64-bit time values, and surprisingly, Christos is wanting to get this in before May. He has a kernel already working with 64-bit time Ts, and it's just now got to do the user line, so not much to do there. Logic shared memory and NAMI tactical changes. David Holland, one of our new developers, although he's had his application in for about 8 years, I think it was, before he actually signed it. He's going to make some changes to NAMI and has been putting out some interesting stuff in our mailing list. If you want to contribute, please do. Please feel free. It's a great opportunity to get in there and see what we're doing on the file system front. So for 6.0, we've got better resource controls planned, improved observability through online crash dumps and remote debugging, and processor and cache topology aware scheduler. And if anybody thinks they can say that better than I do, please come up and say that, because it's a right mouthful. Right, this is the last slide there, so yeah, I promise to go afterwards. 5.0, we expect to branch that at the end of May. We expect to take much less than time for 4.0 to actually get it released. We expect it to take no longer than 6 months. No, really, yeah. Especially as I'm about to be certified. I volunteered myself to be the release manager for 5.0, so I'm standing up here and saying, it's true, I'm a moron. we're looking to branch 6.0 in a year's time, so at the end of May. We expect it to take 6 months, it should be ready in December. So, NetBSD 5.0 and 6.0. Thank you very much for your time.
I'm sorry we don't have time for questions. For those of you who haven't seen the slideshow we're running on Saxon's laptop, a group of people are going to go to the cemetery where Itagen San is interred, and if you want to pay your respects to Itagen San, then you should meet in the lounge in about 5 minutes, and people will take the subway to Gaian and go to the cemetery. And then people will be back here before 6 o'clock for the banquet, which will be in the same room that last night's banquet. So, thank you very much, and we'll see you all at 6.